Earth, our home, a tiny blue dot suspended in a vast, black, cosmic ocean. Every human who ever lived, every love, every war, every dream, every fear, contained on this fragile sphere. All of history fits here. Every story ever told begins on this single point of light, quietly drifting through space. But staying here hides the truth, so we leave. We pull away from Earth's surface, rising past the thin veil of atmosphere that protects us from the vacuum beyond. The sky darkens. Blue fades to black. The familiar curves of continents dissolve into a single, glowing marble. And already, perspective begins to fracture. Earth does not look powerful from here. It looks vulnerable. The first milestone on our journey is the Moon, Earth's only natural companion. It orbits at an average distance of 384,000 kilometers, a number that sounds manageable until you translate it into human terms. Drive a car at a steady 100 kilometers per hour, never stopping, never sleeping, and it would take more than 160 days to arrive. That's half a year of uninterrupted motion just to reach our nearest neighbor. From the Moon, Earth hangs in the sky like a precious artifact. Swirls of blue oceans, streaks of white clouds, patches of green and brown land. No borders, no nations, just one world, glowing softly against an infinite void. This view does something unsettling to the mind. It compresses all of human importance into something that can be covered by a fingertip. And this is still close. We continue outward, leaving the Earth-Moon system behind, and set our sights on the Sun, the gravitational anchor of our solar system. The distance between Earth and the Sun defines a unit astronomers rely on constantly, 1 astronomical unit, or 150 million kilometers. Light, the fastest thing in the universe, needs 8 minutes and 20 seconds to cross this gap. In that time, it could circle Earth more than 7 times. A commercial jet traveling at 900 kilometers per hour would take nearly 19 years to make the same trip. This distance is not empty. It is filled with radiation, charged particles, and invisible forces. The Sun is not just a glowing ball in the sky, it is a raging nuclear furnace, converting millions of tons of mass into energy every second. And somehow, from this staggering distance, it delivers just enough warmth to keep Earth alive. Move a little closer, and oceans boil. A little farther, and the planet freezes. Life exists here because of a razor-thin balance. We break free of Earth's orbit entirely now, pushing deeper into the solar system toward Mars, the red world that has haunted human imagination for centuries. At its closest approach, Mars lies 54.6 million kilometers away. At its farthest, when the planets are on opposite sides of the Sun, the distance stretches to 401 million kilometers. Space is not static. Everything is moving. Everything is shifting. At jet speed, reaching Mars would take more than 50 years. This ever-changing gap is one of the greatest challenges in space exploration. Every rover, every probe sent to Mars must thread a moving needle, launched at the precise moment when geometry, gravity, and timing align. Miss the window, and Mars is simply not there when you arrive. The emptiness between planets is not passive. It actively resists our presence. Still, Mars is only the beginning. We push outward again, beyond the asteroid belt, past the gas giants, until the Sun shrinks into a painfully bright star surrounded by darkness. Eventually, we reach Neptune, the most distant recognized planet in our solar system. Neptune lies about 4.5 billion kilometers from Earth. Sunlight takes 4 hours and 15 minutes to reach it. By the time that light arrives, it is weak, cold, and distant, a pale reminder of a star that once dominated the sky. Neptune marks the edge of familiarity. Beyond it, the solar system dissolves into something harder to define. In 1977, humanity sent a small machine into this darkness, Voyager. 1. A metal body packed with instruments, launched not to conquer space, but to listen. Decades passed. The probe crossed planetary orbits, entered interstellar darkness, and kept going. Today, Voyager 1 has traveled more than 22 billion kilometers from Earth. It is the farthest human-made object in existence, a silent wanderer moving through the cosmic sea. And before it left us forever, Voyager 1 did something extraordinary. In 1990, at the suggestion of astronomer Carl Sagan, the spacecraft turned its camera back toward home. From a distance of nearly 6 billion kilometers, it captured an image that would redefine humanity's self-image forever. Earth appeared as a pale blue dot, less than a pixel, suspended in a sunbeam. Every empire, every religion, every hero and villain, every mother and child, all of it, on that dot. Sagan later reflected that this image was not just scientific data, but a moral lesson. A reminder that our planet is not guaranteed. It is not protected by the universe. It is something we must actively care for, because there is nowhere else to go. Yet Voyager did not stop. Beyond the planets lies the Oort cloud, a vast, theoretical shell of icy debris surrounding the solar system. It may extend as far as 100,000 astronomical units, nearly 1.9 light-years from the Sun. This is the region where comets are born, disturbed by passing stars, and sent plunging inward. It is the last whisper of the Sun's influence, the final echo of its gravitational reach. And then finally we cross an invisible boundary, the heliopause. This is where the Sun's solar wind collides with the interstellar medium and loses. Where our star's influence ends, where interstellar space truly begins. Everything beyond this point is no longer part of the solar system. We have left home completely, and only now does the true scale of the universe begin to reveal itself. Once we cross the heliopause, something subtle but profound changes. There is no explosion, no dramatic visual cue. Space does not suddenly look different. But conceptually, this is the moment humanity becomes a visitor rather than a resident. The Sun, our anchor, our clock, our source of warmth, is no longer in control. Its gravity weakens, its wind fades. We are now adrift in interstellar space. Ahead of us lies our nearest stellar neighbor, Alpha Centauri. On cosmic maps, Alpha Centauri looks close, almost comforting. In reality, it is anything but. The system sits about 41.3 trillion kilometers away. Numbers like that stop meaning anything to the human brain. Astronomers switch units here, abandoning astronomical units and using light years instead. Alpha Centauri is 4.4 light-years from Earth. That means the light reaching us tonight left that star system before smartphones existed, before modern computers, before many of us were born. Even with humanity's fastest spacecraft, the journey is effectively impossible. Voyager 1 travels at about 17 kilometers per second. At that speed, reaching Alpha Centauri would take over 70,000 years. Entire civilizations could rise and collapse in that time. Languages would be born and forgotten. Species could evolve or disappear before the spacecraft ever arrived. This distance exposes a brutal truth. The stars are not stepping stones. They are isolated islands separated by oceans of nothing. And Alpha Centauri is still unimaginably close by galactic standards. We pull back further, zooming out until individual stars blur together into a glowing band stretching across the sky. We are now seeing our home from the inside, the Milky Way galaxy. A spiral structure roughly 100,000 light-years across, containing hundreds of billions of stars, each potentially hosting planets, moons, and stories of their own. Somewhere inside this immense structure, far from the center, tucked into a minor spiral arm, sits our solar system. Not central, not special, just one quiet neighborhood among countless others. But even here, perspective continues to shrink us. There exists a faint, expanding shell around Earth, known as the human radio bubble. It spans roughly 100 light-years in radius. Inside it, our radio transmissions, television broadcasts, radar signals, and accidental electromagnetic noise have leaked into space. Beyond it, silence. To any civilization more than 100 light-years away, Earth is still a mute, unremarkable world. As far as they know, humanity does not exist. That realization lands hard. Our entire technological era, our wars, our music, our science, our voices, has barely brushed the surface of the galaxy. The Milky Way is so vast that over 99.9% of it has never heard us. To the cosmos, our presence is recent, fragile, and almost entirely invisible. We drift outward again. Stars thin out. The dense glow of the Milky Way fades. We exit our galaxy and enter intergalactic space, a realm so empty that even emptiness feels diluted. Here, galaxies are no longer backgrounds, they are destinations. Our galaxy belongs to a modest collection known as the local group. It contains more than 50 galaxies, including spirals like Andromeda and Triangulum, as well as dozens of smaller dwarf galaxies. This entire group spans roughly 10 million light-years. Light takes 10 million years to cross it from end to end. 10 million years. On Earth, that is enough time for entire branches of life to rise and vanish without leaving a trace. Between these galaxies stretches a near-perfect vacuum. No stars, no planets, just thin gas, stray particles, and the faint glow of background radiation left over from the birth of the universe itself. Intergalactic space is not dramatic, it is quiet. And that quietness is what makes it unsettling. From this distance, the Milky Way looks small. We zoom out again. Now we see that the local group is just a fragment of something larger, the Virgo supercluster. This colossal structure spans about 110 million light-years and contains thousands of galaxies, grouped into clusters and subclusters bound together by gravity. Our local group is a minor appendage on its outskirts, barely noticeable. Each galaxy inside Virgo contains billions of stars. Each star may host planets. The scale is no longer astronomical, it is absurd, and yet even Virgo is not the end. We pull back further still, and the universe reveals one of its most astonishing architectures, Laniakea. Laniakea, meaning immense heaven, is a supercluster of superclusters, stretching across more than 500 million light-years. It contains the Virgo supercluster, the Great Attractor, and countless other galaxy groups, all flowing along invisible gravitational currents like cosmic rivers. Within Laniakea are the masses of 100 million billion suns. Entire galactic civilizations, if they exist, would be reduced to statistical noise within this structure. Gravity here is not local, it is collective. Galaxies fall toward common centers of mass, drawn inward by forces so vast they defy intuitive understanding. At the heart of this motion lies the Great Attractor, a mysterious region exerting immense gravitational pull. We cannot see it clearly. Dust and gas obscure it, but we feel it. Our galaxy is moving toward it, carried along with everything else in Laniakea. At this scale, even galaxies are no longer independent actors. They are passengers. And still, this is not the end. We approach the final boundary, not of the universe itself, but of what we can ever observe. The observable universe stretches about 93 billion light-years in diameter. This number feels impossible when paired with another fact. The universe is only 13.8 billion years old. How can something younger than 14 billion years be wider than 90 billion light-years? The answer lies in cosmic expansion. Space itself is stretching. Not galaxies flying through space, but space expanding between them. Some regions of the universe are receding from us faster than the speed of light. Not because they break physics, but because the fabric of space is carrying them away. Those regions are lost to us forever. Beyond the observable universe may lie more galaxies, more superclusters, more wonders, or perhaps something even stranger. We do not know, we cannot know, the universe has placed a horizon around us, not of matter, but of information. And that is where our journey pauses, not because we have reached the edge of everything, but because we have reached the edge of what we can ever see. Standing at the edge of the observable universe, it might feel like the journey should end here. After all, what could possibly exist beyond a boundary defined by the speed of light itself? But this apparent limit is not a wall. It is a horizon. And horizons, by their nature, suggest more beyond them. To understand why, we need to rewind, not in space, but in time. The observable universe is not defined by how far space goes, but by how far information has had time to reach us. Light has a finite speed, and the universe has a finite age. That simple fact shapes everything we can see. When we observe distant galaxies, we are not seeing them as they are now. We are seeing them as they were billions of years ago, frozen snapshots from the deep past. Some of the most distant galaxies visible today emitted their light when the universe was less than 1 billion years old. At that time, stars were just beginning to form, galaxies were smaller and more chaotic, and heavy elements like carbon, oxygen, and iron were still rare. These early galaxies glow faintly, stretched and reddened by cosmic expansion, their light arriving to us exhausted after a journey of unimaginable length. This stretching of light reveals another unsettling truth. The universe has not been expanding at a constant rate. In its earliest moments, shortly after the Big Bang, the universe underwent a phase called inflation, a burst of expansion so violent and rapid that space itself ballooned faster than light could travel. Entire regions of space were flung apart instantly, separated forever before any signal could pass between them. Those regions may still exist. They may be filled with galaxies, stars, and planets, but no information from them will ever reach us. They are not just far away, they are causally disconnected. Even now, expansion continues, and it is accelerating. Driven by something we barely understand, called dark energy, galaxies are being carried away from one another faster and faster. Over time, more and more of the universe will slip beyond our observable horizon. In the far future, distant galaxies will fade from view entirely, leaving future astronomers with a lonely cosmos containing only the remnants of the local group. In other words, we live at a privileged moment in cosmic history, one of the few times when the large-scale structure of the universe is still visible. Zooming out mentally, cosmologists have mapped the universe into a vast cosmic web. Galaxies are not evenly distributed. They cluster along immense filaments of dark matter, stretching across hundreds of millions of light years. Between these filaments lie enormous voids, regions of space almost completely empty, some spanning tens of millions of light years. This web-like structure was shaped by tiny fluctuations in the early universe, amplified over billions of years by gravity. From quantum ripples to galactic superclusters, the universe appears to have grown from the smallest irregularities into the largest structures imaginable. And yet, all of this, the filaments, the voids, the superclusters, is still just the observable portion. What lies beyond may follow the same pattern, or not. Some theories suggest the universe may be spatially infinite, extending forever in all directions. If that is true, then somewhere far beyond our horizon, there could be regions almost identical to ours, galaxies similar to the Milky Way, planets similar to Earth, perhaps even histories that echo our own, diverging only in small details. Other theories propose a multiverse, where our universe is just one bubble among many, each with its own physical laws, constants, and structures. In such scenarios, the universe we inhabit is not the default. It is one outcome among countless possibilities. But here is the critical point. These ideas are not science fiction fantasies. They arise naturally from our best mathematical models of cosmology. The problem is not imagination. It is access. We have no direct way to test what lies beyond the observable universe, and that limitation circles us back to ourselves. Every step of this journey, from Earth to the Moon, from the Sun to Neptune, from Voyager to the Oort cloud, from nearby stars to superclusters, has revealed the same pattern. The farther we go, the smaller we become, not just physically, but historically, culturally, existentially. Human civilization has existed for a few thousand years, modern science for a few hundred, radio communication for barely a century. Against cosmic timescales, this is not even an eye blink, it is a rounding error. And yet, within that tiny window, we have learned enough to reconstruct the universe's past, measure its expansion, and glimpse its possible futures. We are creatures evolved on a small planet around an ordinary star in an unremarkable galaxy, yet capable of comprehending structures hundreds of millions of light-years across. That contradiction is one of the most remarkable facts of existence. The universe does not owe us understanding, and still, piece by piece, it has allowed us to decode its story. But there is still one perspective left to confront, one that turns this entire cosmic scale inward, back toward the question that quietly underlies everything we've seen so far. What does all of this mean for us? That is where the journey continues. If the previous steps of this journey reduced humanity to a speck in space, this part does something even more unsettling. It forces us to confront time itself. Distance is only half the story. The universe is not just big, it is old in ways that strain meaning. The universe is approximately 13.8 billion years old. That number sounds abstract until you compress it. If the entire age of the universe were reduced to a single calendar year, all of recorded human history would occupy the last fraction of the final second before midnight on December 31st. Agriculture, writing, science, cities, nations, everything we consider foundational, appears almost instantly, then vanishes. For most of cosmic history, there were no planets at all. After the Big Bang, the universe was simple and violent: hydrogen, helium, darkness, and heat. The first stars did not ignite until hundreds of millions of years later. These early stars were massive, short-lived, and unstable. They lived fast and died young, exploding as supernovae and seeding the universe with heavier elements: carbon, oxygen, silicon, iron. Without those deaths, planets like Earth could never have formed. Every atom in your body heavier than hydrogen was forged inside a star that no longer exists. This means something crucial. Life could not have arisen early in the universe. There simply weren't enough elements. The cosmos had to mature. It had to recycle matter through multiple generations of stars before chemistry became rich enough to support biology. Only after billions of years did galaxies settle into stable forms. Only then did long-lived stars like our Sun become common. Only then did planets with solid surfaces, oceans, and atmospheres become possible. We did not arrive late. We arrived when it finally became possible. But time does not stop here. Stars like the Sun live about 10 billion years. Red dwarfs, the most common stars in the universe, can live trillions of years. That means most habitable planets that will ever exist have not even formed yet. The universe is still in its early chapters when it comes to life. This flips a disturbing assumption on its head. We tend to imagine ourselves as latecomers, living in a universe that has already had countless chances to produce intelligence. But statistically, it is more likely that intelligent life is rare right now simply because the universe hasn't had enough time yet. If intelligence requires stability, complexity, and long evolutionary periods, then the most fertile era for life may lie ahead, not behind us. And this leads to a deeply uncomfortable thought. If intelligent civilizations are rare now, but more common in the future, then we might be early, not special, not chosen, just early. This reframes one of the most famous questions in science. Where is everybody? The apparent silence of the universe, sometimes called the Fermi paradox, may not be a mystery at all. It may simply be timing. Civilizations may arise sparsely across cosmic time, separated not only by distance, but by billions of years. Two intelligent species could exist in the same galaxy and never overlap. One could rise and fall before the other ever evolves eyes. From this perspective, the vast emptiness we observe is not evidence of loneliness. It may be evidence of patience. And patience is something the universe has in abundance. Zooming back in slightly, we realize something else. While the universe expands on the largest scales, local gravity still wins. Galaxies merge, stars form, planets assemble. Complexity continues despite cosmic stretching. Our own galaxy will eventually collide with Andromeda in about 4 billion years. This will not be a violent crash of stars, but a slow gravitational dance lasting hundreds of millions of years. Solar systems will mostly survive. The night sky, however, will transform completely. New stars will ignite. Old ones will be flung outward. Entire stellar neighborhoods will be rearranged. And if life still exists on Earth, or whatever remains of it, it will witness a sky no human has ever imagined. Even farther ahead lies a darker future. Star formation will slow. Gas will run out. Galaxies will age. Eventually, the universe will enter what physicists call the degenerate era, a time dominated by stellar remnants, white dwarfs, neutron stars, black holes. Light will become rare. Energy gradients will flatten. Complexity will struggle. And yet, even then, time continues. Black holes evaporate over unimaginable spans through Hawking radiation. The universe keeps thinning, cooling, stretching. Whether it ends in heat death, decay, or something stranger is still unknown. What matters is this: the universe is not static. It is a process. And we are not observers standing outside it. We are part of its timeline, temporary, fragile, but undeniably real. Everything we have explored so far, the distances, the structures, the ages, leads inevitably to a single realization. Understanding the universe is inseparable from understanding our place within it. And there is still one final layer left to confront. Not space, not time. Meaning. After crossing distances so large they erase intuition, and timelines so deep they dwarf human memory, the journey finally slows. Not because the universe ends, but because our perspective changes. Up to this point, everything has been about scale. Bigger distances, older ages, larger structures. Each step outward reduced Earth, then the Sun, then the galaxy into something smaller and smaller, until even superclusters felt like brief patterns in a much larger expanse. But scale alone is not the final lesson. The final lesson is contrast. The universe is vast beyond comprehension, yet almost all of it is empty. It is ancient, yet for most of its existence it was dark and lifeless. It follows precise physical laws, yet those same laws accidentally allowed complexity to arise. Not everywhere, not easily, but at least once. On one small planet, orbiting an ordinary star, chemistry crossed a threshold. Molecules began to copy themselves. Errors accumulated. Selection acted. Over billions of years, matter organized itself into systems capable of perception, memory, fear, wonder, and eventually understanding. That is not something distance can diminish. When we say Earth is insignificant because it is small, we miss the point. Size is not relevance. The universe is filled with objects larger, older, and more powerful than anything here. But none of them are known to ask questions. None of them are known to wonder what lies beyond the observable horizon. None of them are known to turn instruments back toward themselves and reflect. The universe did not need to produce life. It did not need to produce consciousness. And yet, here it is. That realization reframes everything we've seen. The moon is no longer just a distance marker. The sun is no longer just a furnace. Voyager is no longer just a machine drifting through darkness. They become extensions of a single phenomenon, the universe examining itself from one rare vantage point. We often ask whether humanity matters in a universe this large. That question assumes meaning must come from size, permanence, or dominance, but the universe itself offers no such criteria. It simply unfolds according to its laws. Meaning, if it exists at all, emerges locally, where complexity allows it. And complexity is fragile. Earth's history is filled with near misses, asteroid impacts, mass extinctions, climate collapses. Life survived not because the universe protected it, but because it adapted fast enough. Intelligence survived not because it was inevitable, but because it happened to persist. Nothing guarantees it will continue. That is why the pale blue dot still matters. Not because it is central, but because it is rare. Not because it is eternal, but because it is temporary. The universe will go on expanding long after Earth is gone. Galaxies will drift apart. Stars will burn out. Even black holes will fade. But the fact that, for a brief window of cosmic time, the universe could be observed, measured, and understood from within, that fact cannot be erased. We are not the destination of the universe. We are a moment in its process. And that moment is precious precisely because it does not last. The journey across the cosmos does not end with answers. It ends with responsibility. If this is the only place where the universe is known to think, then what happens here matters, not on a cosmic scale, but on the only scale where meaning exists at all. For now, Earth remains the point where the universe became aware of itself, and until that changes, this tiny blue dot is not just our home. It is our entire known chapter in the story of everything.